Okay, guys, so welcome to our, I think it's our second to last review session, actually. I probably will do one next week, and either I'll do the parametric polar thing, or maybe I'll just see what you have questions on. You know, I haven't done that yet at all. So if you have questions on that, or maybe a recent practice test or whatever, next week at this time will be in the heart of chapter or 2014 exam, which is just a year old. So okay, so anyway, again, I got some notes here from Lynch, like I have for the areas and volumes, and Mr. Lynch kind of spelled it out here. We have the nth term divergence test. That's just basically when you do a limit to see if the limit's zero. If the limit's not zero, then you know automatically it has to diverge. But that doesn't help us at all with convergence, unfortunately. Geometric series is a very special kind, I'm teaching my algebra, my pre-calc kids that now, so they know it really well. But it does show up quite a bit. Let me say something about that real quick. On the AP test, if they say find the sum, chances are it's a geometric, because there's so many different kinds of series, and we really don't know how to find the sums of them. Some of them are beyond the greatest minds, But the geometrics add up well, and we can predict how they add up. It's just A1 over 1 minus R, right? A1 over 1 minus R. Okay, and then P series, only when P is greater than 1, will the function attack the x-axis fast enough to pinch off a finite volume. Okay? And then the integral test is a cool one, if you're good at integrating. But it's a nice one because if you can integrate the function and find an area under it, then that would imply that this series has a sum. Okay? So I just want to draw a quick visual for that particular case, the integral test. What we're saying is if there is a blue area under this curve, if this area is actually finite, and 100 or 10 or 4, if that area exists, then we can also assume that these little sticks, which are located at every counting number, can be glued together to form one meaningful stick. Okay? So here's the connection between integrals and series. Either the area exists and it's finite, so all these little red sticks can glue together to form a long stick that can actually be measured, or the blue area is infinite, and the red sticks, unfortunately, keep stacking together and it gets longer and longer and longer forever. Okay? So whatever the integral does, the sticks will do. Finding the blue area is not the same thing as finding the length of the long red stick. There's no way that's the same amount, right? The length of the long red stick is not going to be the blue area. But I'm saying if there is a blue area, then the red stick does exist and has a measurement. If there is no blue area and it's infinite, then so is the stick. If that makes sense. That's the best way I can think of to explain the integral test. And before you dismiss it and say, I stink at integrals, know that 1 over n is our harmonic series. And one of the reasons we believe it diverges is because the integral does. So it's actually a really important one, and it helped us to understand 1 over n. 1 over n has an interesting history. It was very elusive for a very long time. Mathematicians weren't sure what it would do. Alternating series test. As I've been grading through period 5's series exam, I noticed that most people are just doing a limit. So they're kind of doing the second part of the sentence. They're finding the limit of a sub n, and they're saying, oh, it comes out 0. But you also need to show that it's decreasing monotonically. So besides the fact that the little red sticks are getting closer and closer to 0, they also have to be getting shorter and shorter as you go. Because some things go to 0, but they oscillate. They go up, down, and the behavior isn't that clear. So you really have to have diminishing or decreasing. That's what this is saying. And limit is 0. That's pretty important. All right. Ratio test is everybody's go-to probably. When does it not really work for us? L equals 1. Why is it a go-to? It's because the absolute values are awesome. Okay? The absolute values take away that darn alternator, okay? Or any negatives LCT, those are really meant for positive expressions. You can see that right here. See? Look at the assumptions. Look at these assumptions. F is positive, A sub n is positive, A sub n is less than B sub n, both have greater than or equal to 0. Right? A is positive, B is positive, you're comparing two positive series. This is a problem if you have a series that has negatives in it and it's non-alternating, then you would want to go to ratio test because it just forgives that negative stuff. See, that's kind of cool. And the other thing is you don't have to pick something that is comparable. Like you don't have to do that at all. You just compare the series unto itself. But like all go-tos, there's a drawback. If L comes out to 1, you have to start all over again, right? So most of the series we've done in this class can be solved with these tests here. And what does this testing help us find? Only if it converges or diverges. It does not tell us anything about what it converges to, right? Okay. So just a quick few comments there on that. LCT is not a bad test, by the way. It's a pretty good test. Okay, another skill besides knowing if something converges that you need to have is you have to be able to find the sum of a geometric, and that's, of course, when R is between 0 and 1. I will warn you, if you have a geometric series and R is bigger than 1 or even equal to 1, this formula will give you a number. Okay? But it doesn't mean anything. So do not ever use this formula when R is 1 or 2. Even if it gives you an answer, it's meaningless. Okay, that's really important. Formula's not going to, when you plug in a number and type it into your calculator, the calculator's not going to say, oh, you performed an illegal operation. No, it'll give you a number. You just have to know it doesn't mean anything. You have to have R less than 1 or greater than negative 1. And then determine the radius of interval convergence. That's just using the ratio test, basically, set it all up. And I've noticed you guys are actually pretty strong at this. Maybe it's because it's an algorithm. It's something you actually do on this. You do the same thing every problem. You know, that can make problems go smoother for some people. There are two ways, though, that you can express your answer. And this is something I didn't really cover in class. It's not like entirely necessary that I say this, but I have found it helpful every now and then. Sometimes you'll get all the way down to the end of your problem, and you'll have something like this. X minus 3, absolute value, is less than 4. And you know you're supposed to continue if you're looking for that interval. But listen, you already have the radius. Okay? The radius is 4. So you don't have to actually pursue this any further. If you were asked for a radius of convergence, the answer is 4. Here's the logic. In a moment, you're going to put a negative 4. I'm sorry, the radius is 3. Right? No, the center is 3, the radius is 4. I said it right the first time. If you sandwich this between negative 4 and 4, you're going to end up adding that 3, and you're going to get 3 plus 4, 3 minus 4. Sounds like 3 is the center, and it goes 4 out on each side, you see. So this is basically your center. It's like your right shift, you know. And then there is your radius. It's right there. If you're asked radius of convergence, save yourself 20 seconds, and don't do the rest of the problem. You've got your radius, you've got your center. So I'll label those for you, just so you have them on your paper. This is your center. This is your radius. Did I teach that in class? No, because I knew you'd just pursue it to the end anyway. I didn't really test you on conditional and absolute convergence either, but just know this. You don't have to really read all that down there. Basically, think about the harmonic series, right? We all know the harmonic series is divergent. But if you put an alternator on it, it actually converges. Okay? So this is a classic example of conditional convergence. You would expect the harmonic series to just always diverge, but not if it's alternating. So that means it's sometimes converging when it has the alternator. Okay? Now other series will always converge. For example, this guy diverges, right? But if you stick that alternator in, suddenly it converges. So that's conditional. But obviously if there was an n squared on this, it would converge either way. So you see what I'm saying? This is going to be converging in both cases now, because I put this square on the bottom, and it's now a p series, see? The first one's a p series, p equals 2. So this would be absolute convergence. Absolute convergence just means even the non-negative version converges. Now, why is it more likely that something with negatives would converge? Why is it more likely that something with negatives would converge? Yeah, Jacob?
Because the negative will cancel out with some of the positives, making it fewer positive terms.
Yeah, that's right. So we would expect alternating stuff to converge more often because of all those minus signs. It keeps that value finite, see? But with all pluses, it's rare, it's more rare, I should say, to see convergence. Okay? But if it does converge, if any series you're testing converges, then it's absolutely convergent. If the absolute value of a series converges, then it certainly will without the absolute value. You can memorize these here. You should. I noticed some of you didn't on your last exam. But it could just be that you weren't aware that you needed to. So I tried to send you a warning the night before. I said, here, memorize these. And some people saw it, some people did. But these are just classics. And you know, you really don't have to memorize the cosine one. Why not? It's just the derivative of the sine one. Take the derivative of the second one, you get the third. Okay, you can also, let's skip bullet 6 for a minute. You can differentiate or anti-differentiate Taylor series, or even Maclaurin series. Oh, by the way, some of you aren't sure what Maclaurin means. I can tell because I had you construct a Maclaurin series, and you didn't know to plug in A equals 0. So you have A in all your work, but you didn't. So once you wrote, what's A? Like you never told us A, but it's Maclaurin. That means A is 0. Okay. But anyway, your ones that you memorized up above, the sine and the cosine, you can take their derivatives and produce new ones, or anti-derivatives, whatever. You can even add or even substitute into a Maclaurin series. So, like if you go back to sine of x squared, or e to the x squared. If somebody ever asks you, hey, make a series for me, would you? E to the x squared. Don't even stress about it. Just take this thing and just stick in an x squared instead of an x. It's that simple. Now, if you are not at 0, if it doesn't say Maclaurin, or if it says at a equals 1, that will not work, because you're assuming when you plug in an x squared, you're assuming that it's like x minus 0 squared. So you've got a center of 0 here when you substitute that in. So you've got to be really careful. You just have to redo the Taylor series, f prime at 1 plus, f of 1 plus f prime of 1, x minus 1, that sort of thing. If it's not at 0, you just have to start over and rebuild. Yeah?
If you substitute an x squared for like this sigma, would you substitute x squared in for this, like the expansion of it as well?
Yeah. So you could change this to, you could change this guy, I think you're asking, you could just change that to an x squared.
Yeah.
This would become an x to the 4th. This would become an x to the 6th. That's exactly right.
Okay.
It's that simple. Comment or question?
Yeah, it's actually about the exam today.
Today's test.
Huh?
Yeah, go ahead.
We had this problem where it was like there was a Taylor series centered around x equals 6, and it said find the coefficient of the Taylor series, the 6th power term.
6th power or 6th order?
Yeah, 6th order.
They don't always mean the same thing.
You have to find the coefficient of that term, and you have to take that would be the nth derivative of f over n factorial. But that means you have to take 6 derivatives, and by the time I got to the 6th one, I had like a 5-digit number, and it was a non-calculated problem. So was I doing that wrong?
Mr. Short, it was actually x to the 6th, not the 6th term. Like
It was the x to the 6th term?
Find the coefficient of the x to the 6th term.
Okay.
So it was only like 3 derivatives because.
Wait, we went to 0.
Okay, so let's say that, Jacob, this was e to the x squared. This would have been x squared, and this would have been x to the 4th, x to the 6th would have been here. So my guess is, and Jenna seems to confirm it, is it was actually on the 3rd derivative that the x to the 6th term pops up. I'm sorry, yeah, you did way too many derivatives on that. I can see myself doing that. Get it? So he did 6 derivatives, but with the x squared, it was actually doubling.
Well, no, it said Taylor series though. So Taylor series go up by 1 exponent each time.
But that would be called 6th order then. If you're looking for the x to the 6th term, that could happen on the 3rd order. where you have your third derivative.
Third order. Third order.
Order
is
means
term.
order isn't term. Order means how many derivatives you took. So if you took 3 derivatives, that's called third order. Now x to the 6th might pop up, like on this problem. Here. On this problem, it is on the third derivative that x to the 4th pops up, see? I'm sorry, on the third derivative, x to the 6th pops up. So, that can happen.
Would it be okay if I looked at that problem again, or am I not allowed?
Sure. No, you can. It should be sitting right there on your desk. Okay. So anyway, what I'm saying is you can substitute into these and differentiate them and integrate them. So you can even leave them in sigma form when you take the derivatives. It takes a little practice, but just ignore all the n garbage and mess around with the x. Okay, back to bullet 6. Deriving a Taylor polynomial, you just basically use this formula. And in our textbook, they don't use P sub n, they use capital T sub n, I think. Or maybe they do use P in our book. But I've seen on the AP test they use just a capital P or just a capital T. And it represents a polynomial that approximates a function. And basically, they also don't use C, they use A, lowercase a. But that shouldn't mess us up too much. So what's the difference between a Taylor polynomial and a Maclaurin series? Taylor polynomial actually stops. See that? It actually stops. It has, n terms. It doesn't go on forever. The Taylor series and the Maclaurin series, those guys go on forever. Literally never stopping. A Taylor polynomial truncates after a certain number of terms. The more terms you have, the more accurately this polynomial models a sine wave or whatever curve it is. But it's just a formula. So let's go down and look further here. Errors. Error is one of the gnarliest subjects of the year. Fortunately for us, there's only 2 types of error problems on the AP exam. One is alternating series error, or alternating series remainder, and that is pretty easy. This is kind of complicated, but basically just highlight a sub n plus 1. A sub n plus 1. Right here, this guy. What this is saying is, when you add up, let's say, the first 3 terms of a series, an alternating series, and you want to know how far off is this from the actual sum, well, check the 4th term. The 4th term is the 4th term, but it's also the error. It's the error in using the first 3 terms. I'll do a quick example of that. So you might have a series that looks like this, -1 to the n, 2 to the n, over e to the n plus 5, okay? And this is your series. And it's clearly alternating because of that -1 to the n. The error in using the n equals 4 term, or I should say the error in using the terms n equals 0 through n equals 4, is simply this right here. You can do absolute value. Notice what I'm doing. I'm plugging in 5 into my summand, and I end up getting 32 over e to the 5th plus 5. 32 over e to the 5th plus 5, which I think I'll go ahead and get the decimal for. So you might say, well, what does this number mean? Well, it's the next term. It's the term after the ones I didn't use. I only used -1 to the 0, 2 to the 0 over e to the 0 plus 5, plus -1 to the 1, 2 to the 1 over e to the 1 plus 5. I used all of these all the way up through the 4th one. Which obviously is not the entire sum. I mean, it's supposed to go on forever, but I don't have the free time to go on forever. So I'll stop here. How far off am I? Well, it's only 0.2. The very next term also tells me how far off I am. Interesting. It's weird that the 5th term is also the 4th error. But that's exactly how it works. And this only, unfortunately, works with alternating series. So this would have been a really easy one on my test. When you get back your series test, it's the second to last problem, I think. It's the second to last problem on the second page. Yeah, you'll see it. It's a pretty easy problem. It's a little bit different numbers, but the Lagrange error, that basically tells us, let's say you have a function, I don't know, it could be a sine wave, whatever, and you've created this Taylor polynomial. Let's just say it's, I don't know, T3 or something. That means third order Taylor. There's a little bit of gap in here. So let's say that I told you that we were interested in going from 0 to pi over 2. What's the biggest this little gap ever gets here in this region between 0 and pi over 2? Well, it probably happens at the far right of the interval. You can see that that's when things start to sort of diverge apart. And if you check that little gap right there, if you can get that little gap, that's how much error you have when you approximate, you know, t of pi over 2 and f of pi over 2. There's a gap there. And that gap can be found by using this horrible formula. The method we use in class has slightly different symbols. So I think this is from the Larson textbook. But that gap right there is going to be basically less than or equal to, and then we just use the n plus first derivative evaluated at z over the n plus first factorial times x minus a to the n plus 1. So it's kind of, again, it's kind of the next term. In this case, that gap would be f3 plus 1, 3 plus 1 factorial, and then x minus a to the 3 plus 1. So in this 3, in this example I've drawn, you can put those in if you want. So this would be a fourth derivative, a fourth factorial, and a fourth power on that binomial term. Okay? But that will tell you the largest gap that we've got in the interval. Now you have to pick your own x and your own z. That's the hard part. And this is after finding four derivatives. So you got to pick the x and the z that would make this number the biggest. So usually that's just an endpoint. Like in this problem, you would probably just pick pi over 2 because that's where everything diverges the most. And also, it makes this expression as large as possible, as you'll see. If your f is like a cosine, or sorry, if your derivative is a cosine or something, you probably want to pick something real close to 0 because that's sort of when cosine maxes out. If your fourth derivative is like a sine, then you're going to want to pick something far away from 0, you know, relatively within the first fourth period, that would cause that sine to grow as much as possible. So we'll see more examples later in the lesson. So, okay, but it's also a kind of a formula. It's just a little hard to use. Some students have asked for clarification on how to properly answer questions about divergence or convergence. For example, they get to a G-series problem, and they just want to know, how do I write my answer? Well, in this problem here, it's a little hard for you to see on the screen, but you can see it right there on your paper. This is actually a geometric series. A little hard to see it at first, but when you first write out the first term, you plug in 1, you end up with 2 to the 2 times 3 to the 0. Not very interesting. When you plug in 2, you get 2 to the 4th times 3 to the minus 1. If you plug in 3, you get 2 to the 6th times 3 to the minus 2. You might not see it yet, but this is really just 4, 16 thirds, 64 ninths. And now you look at it and you say, oh, I see it. The top is being multiplied by 4, and the bottom is multiplied by 3. This really is a geometric. Okay? So if you're going to state that this is convergent, and you have to defend yourself, you should write it in a convergent format so that the grader knows that you know what a convergent G-series is. So you would just write, all right, so this is first term times r to the n minus 1. Write it like this, and then make your defense. Say, hey, look, it's a geometric series with first term 4 and common ratio Reading it in this original form does not help the grader see that you can see that R is 4/3. Does that make sense? You need to write it like this, and then you can make your defense. This thing is divergent, actually, isn't it? Did I say converge? This one's divergent. R is too big. R is bigger than 1. Greater than or equal to 1, it always diverges. And then with P-series stuff, some people want to know, hey, is it okay to treat 5 over n cubed the same way we treat 1 over n cubed? This is a very good question. Will the graders be upset at you if you say something like 5 over n cubed is a convergent P-series? Well, every textbook defines a P-series as 1 over n to the p, not 5 over n to the p. See? So is it okay to have that 5 there? The answer is yes. It is okay to have the 5 there. And to pull it out front and to say 5 times 1 over n cubed is still convergent. 1 over n cubed converges, comes out to a value. I then multiply by 5. It's still a convergent value. So don't stress out about the 5 on top and wonder what to do with it. Just leave it in your work or pull it out front. Remember also that the divergence test is your first thought always. Whenever you're given, does this series converge, the first thing you should do is take a limit. If the limit is not 0, you put diverge, and you move on. Okay? If the limit is 0, what does that mean? Another test, because it might converge. Yeah. All right. Next is the integral test. We already talked about that. Comparison test. How do you pick a comparison series for something like 1 over 2 to the n plus 1? Well, probably just pick 1 over 2 to the n. You know, take a simpler version of what you're looking at, and hopefully it works out for you. If not, try again. But like on this problem, 1 over 2 to the n is technically a G series. It goes 1/2, 1/4, 1/8, 1/16. And it's convergent because R is a half. Since the extra plus 1 on the bottom is only going to make your series you're studying smaller, it's less than a convergent G series. So this would be a classic example. Now, do you have to defend in your writing why 1 over 2 to the n converges? Or can you just state that it's a known convergent? Do you guys understand the question? Listen to the question. How do we know if we're supposed to, if we're going to be comparing 1 over 2 to the n to plus 1 to 1 over 2 to the n, do we have to defend that 1 over 2 to the n is convergent? Do we have to show proof or something for that? No. A convergent G series, the math community, they all know, they even have a name for it, right? Convergent G series means R is less than 1. So you do not have to defend that it is convergent G series. You just have to say that it's a convergent G series, okay? You don't have to say, well, R equals a half always converges because, and then write some long proof. No. We all agree R equals half converges. Don't feel obligated to show the graders that you know why 1/2 to the n converges. It's a convergent G series. Just state it. Okay, they'll accept it. Limit comparison test. Again, if I was doing limit comparison test, I would probably pick the exact same series as the DCT. I just have to keep in mind that I'm going to be doing a limit problem. So sometimes limit problems can be very challenging. So here is basically a similar problem. I would probably not pick 1 over 2n. I'd probably just pick 1 over n. And if you put that into ratio with 1 over 2n plus 1, and you run that limit, you'll get a half. Anytime you get a real number greater than 0, then automatically it means these two behave the same way. So notice the disk came out to a half. That's a real number. Back in chapter 8, we said the functions grow the same. In chapter 9, we say the series behave the same. So what does 1 over n do? It's divergent. So what is 1 over 2n plus 1 going to do? It's divergent. They agree in their behavior. So that's a neat little example there too. How to use LCT. I already talked about AST and absolute convergence and the ratio test you're already good at. Now here is a ton of examples which I don't really intend to do for you. And the answers are on the next page anyway, so try not to peek if you get a chance to try this sometime. Mr. Lynch used to give this worksheet out, and he called it Converge or Die. This is his Converge or Die worksheet. I don't know if he made these up or borrowed them from somewhere, so the best I can say is I got it from Mr. Lynch. And I don't know where he got it from. But basically, I would take out all the alternators, because you can use AST on all of those. And then I would also look for other types of familiar ones. Like, for example, if there's something to the end, see that 14? That's a G series. See that? Where's another one that might be a G series? Anyone see one? You see one?
Oh, no, I was going to ask a question.
Oh, okay.
Do we this probably sounds like a stupid question, but do we have to be, we only have to be that verbose with our logic on the FRQs, right? Like, they're not going to grade the fruit or the...
Yeah, that's right. They do not grade the multiple choice in any way, shape, or form.
Okay.
They look at the Scantron. So, some of those multiple choice series ones you can get away with whatever. Notice that cos n pi is actually an alternator. Cos n pi is one of the alternators I taught you. -1 to the n, -1, then -1, cos n pi, those are all alternators. So this would be an AST candidate right here. Okay? Same with this one, sine of odd multiples of pi over 2. The first odd multiple of pi over 2 is 1 pi over 2. So this comes out to uno. And then it goes 3 pi over 2, 5 pi over 2, 7 pi over 2. That's just going +1, -1, +1, -1. This is an alternating series, believe it or not. Both 27 and 28 are. Okay? Anything with a factorial, if I were you, I'd use the ratio test. Okay? And anything that has a difference of 2 fractions, I would use telescoping logic. So what does that mean? That means you write out the first few terms, maybe the first 8 actually, and then you'll see almost everything's canceling out. Okay? You guys want to try 30 real quick? Yeah, tons of stuff cancels out. I think that was telescoping. It certainly looks like it. Or you can put it all together into one series, one fraction too. So write out like the first 10 and the last few before the nth term. Basically, the 1/3 cancels out, the 1/4 cancels out, the 1/5 cancels out, right? The 1/6 cancels out. Let me switch colors here. I'll switch colors when I get to in terms that have partners that we don't see. Like, you don't see the positive 1/7 because I didn't bother to write it, but it will happen. Notice that even the 1 over n plus 1 cancels out. So you're not left with a whole lot of stuff. You're kind of just left with a lonely halfer in the front. Hello, Mr. Half. Sorry you have no partner. And then he says back to us, that's okay, I didn't get canceled. I survived. Don't apologize to me. No partner, but he survived. And this guy survived. So now you can kind of see what survived, and you can actually compile it, put it together, and take its limit. That will give you the convergence value. Okay? So what's just survived is called the S sub n, the partial sum formula. That's the survivor here. I think I did that right. Oh, there's a 1 over n there too. Do you think he should cancel? Think he'll cancel? Yeah, the term right before this is 1 over n minus 1 minus 1 over n, so that 1 over n cancels as well. Yeah, question?
So are you like done with your telescoping series when you do like n equals n? Is that like your last term that you would plug in?
First of all, you'll never have to do this on the AP test. Second of all, I need to think about that before I answer with an absolute yes or no. Let me think about that some more. I don't want to say yes and be wrong. And are you wondering if we should look at more terms?
Yeah, because like when you stop, you get like 1 over n plus 1 minus 1 over n plus 2, and that's like the initial series that they give you. So like, would you stop like when you get to like n equals n?
So what just survived is this thing. I hope I did that right and didn't miss anything. But that's called Sn, and that's the nth partial sum. What that guy's job is to add up the first 100 terms for you, or whatever. That's kind of cool. And then if you take its limit, make sure you put it into one fraction first. If you take its limit as it goes to infinity, it'll tell you what everything adds up to. I think that's how how that one works. But yeah, you can stop at n. That gives you a formula, and then you take n goes to infinity. I'm just reluctant to circle this as a final answer because I didn't really check that I got all my terms right. I think I did, but here's what you have to do on the AP test. Okay, you just have to know that this is telescoping and that telescoping series converge. That's it. Okay, I don't even think I've seen a telescoping one anyway. But if you have to do anything with a telescoping, it would just be to state it's convergent. So I'll look for those canceling terms. So try this sometime when you get a chance. You're probably better at it than you think. And all the answers are right here, including reasons. Oh, by the way, you might try limit comparison. You might try DCT and have some trouble, but limit comparison test might bail you out. Okay? So LCT is not everyone's favorite, but it sometimes works when you cannot figure out a DCT comparison. And also, just because Mr. Lynch says it converges by the ratio test doesn't mean that's the only test you could have used. That's just the test he wanted to use, you see, when he made the worksheet. Answer key. Does that make sense? So you might actually be able to prove using other tests. These are just some sample answers. Okay, let's take a look at some FRQs that have shown up the last few years. Here's 2010. I don't think I've shown you this one yet, right? Okay. So it says here, the function defined above has derivatives of all orders. Now, why would they tell you that? It's important because you guys are probably going to end up using Taylor's theorem at some point and taking, 3, 4, 5, 6 derivatives. So you need to be told ahead of time that that's allowed. Okay? So maybe you glossed over that, but it's just probably suggesting you'll be finding several derivatives. Let g be the function defined in this way. So always read your stem because you're going to need that g, right? Although not for part A. For part A, you're just doing Taylor's series for cosine. Wait a minute, I thought we memorized that. Write the first 3 non-zero terms in the general term of the Taylor series for cosine at x equals 0. You've memorized that. That's your Maclaurin series. So that has nothing to do with the stem. It's just going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. There's your first 3 terms. And here's your nth term. Negative 1 to the n, x to the 2n, 2n factorial. Is that the last term? No. Taylor series going forever, but that's the nth term. So make sure you have this dot, dot, dot. Okay? Use this series now to write the first 3 non-zero terms in the general term of f. Okay, so now we're on to using the stem above. Okay, so look at f. I'll do my part A up here. F is basically cosine x, that's all this, minus 1. It says f is cosine x minus 1 all over x squared. Well, what happens when you take this red beast? I forgot my last dot, dot, dot. What happens when you take this red beast and you subtract 1? Look, this is cosine, right? What happens when you subtract 1? You just lose the first term. Right? So goodbye 1, because we're subtracting 1, see? So this blue 1 cancels the red 1. What happens then when you divide by x squared? What happens when you divide by x squared? You're going to lose 2 powers of x in every single one of the terms, right? Okay, so what we're saying is f is basically cosine without that 1. That's canceling out. Then we're going to divide every term by x squared. So now let's write our f. The 1 canceled out. The x squared is being divided out. So what's x, what's my first term? It's actually just basically right here. I'll highlight it with a green highlighter. It's right here. It's this over x squared. So that's just minus 1 over 2 factorial. Then the next term is the x to the 4th over 4 factorial divided by x squared. So that's just going to be basically x squared over 4 factorial. That's your second term. And it's positive. And then I want the first 3 non-zero terms of f. Oh, I kind of regret when I wrote my cosine, I only did the first 3. Because now I need another one here. But maybe you can pick up on the pattern already. What's the next term in the cosine expansion? Positive or negative? Negative, and it's x to the 6th over 6 factorial, but we're dividing by x squared, so it's x to the 4th over 6 factorial, and it's negative. So they're very clever how they asked this. They did not have you write the first 3 terms, the first 4 terms of cosine, but you needed that 4th term to get the 3rd term of f. Interesting. But that's the answer for any values except x equals 0. And then the piecewise function finishes down here. So this is actually the answer for part A, along with the red down here. So I just boxed all my answers. The first 3 terms of cosine and the nth term of cosine. Here's f, which is basically cosine without the 1 and diminished by 2 powers of x. And it's a piecewise function, so don't forget to finish writing it. Okay, so part B, on to other things. Use the Taylor series for f about x equals 0, found in part A, to determine whether f has a relative max or min, or neither, at x equals 0. It sounds like we're going to need to take the derivative of f. So this is a rare case where if you did part A wrong, you're toast. Okay, you're going to get part B wrong. So we're going to try to take the derivative to see if f has a relative max, min, or neither at 0. Why don't you guys try that real quick?
Wait, what are we taking the derivative of? Which part?
Both. With the piecewise function, you take the derivative of all the parts,
Okay, so whatever's in
and you just keep the domains. Although, for like less than or equals, you just make them strictly less thans. So we don't really have any of those here, but you'll be taking the derivative of both parts of this. And you know what I forgot to write in here was my general term. So this last red divided by x squared, I forgot to write. There's one little term I forgot to write. It's right here. I forgot to write x to the 2n minus 2 over 2n factorial. Okay, I'll highlight the one I just wrote in case you just tuned in. I forgot to write that term. That's the general term of f. Okay, so you got to take the derivative to do part B now. What is f prime? Now we're going about x equals 0. So that means actually everywhere near x equals 0, but not to 0. If I said, look at all the people around about me. I'm not talking to myself, right? I'm talking about everyone around me. So you probably couldn't just ignore this part, Jenna, because this is at x equals 0, and it says about x equals 0. So you can just use this first line, technically. Does that answer your question?
Yeah,
Yeah.
I wasn't sure if we were doing the derivative of the original or the thing we just made.
Well, it says in part A, although I imagine they give us the same answer, it says use the part A answer.
Yeah.
Use the Taylor series, it says.
Why did we add 1 in the first place?
What do When did I add 1?
Like, what was the first term? Like, 'cause you had.
Cosine is something you memorize, and it's right here. It has a +1 at the very beginning. Is that your question? And then I put it in up here.
Okay, never mind.
Did you why did I take away 1?
Yeah, I see it.
It's because that's the way f was defined. Yeah. F was defined as cosine, take away the 1, divide all the terms by x squared. Okay, take a moment and find the derivative. And then we're going to try and see if f has a relative min or a max, or maybe neither. Okay, so term by term, your derivative, the first term is 1 over 2 factorial. The derivative, that's 0, that's a constant. And then you have the x squared over 4 factorial. So that just basically comes out, since this is x squared over 24, the derivative, that's just going to be basically x over 12. It's positive. So this is just a 1/12 x. And then this next term is minus x to the 4th over 6 factorial. Isn't that 720? Yeah, so it's going to basically be, when you bring down the 4, it's going to be minus 180 on the bottom. So minus x cubed over 180. Minus x cubed over 180. And so on. And then your general term, you're going to bring down the 2n minus 2. And you're going to have x to the 2n minus 3. And this is all over 2n factorial. And we don't need to take the derivative at 0 because we're talking about 0, around 0. Okay, so now what happens if you plug in 0 into your derivative? What happens? What happens to every single term? You get 0. What does that mean? The slope is what? 0. So no wonder they're asking us what kind of critical point it is. It's definitely a critical point, right? So notice that f prime of 0 is certainly 0, no doubt about it. But what kind of horizontal tangent is it? Is it a peak where the graph flattens out? Is it a valley? Is it an inflection point? What's going on here? So what's one way we could test a function to see what kind of critical point it is? Plugging them on the left, plugging them on the right. That might be fairly challenging. Don't you agree? What's another way we can test whether a horizontal tangent is a minimum or maximum? Why don't we take the derivative one more time? Because the second derivative will tell us concavity, right? And if the concavity is positive at a horizontal tangent, it means the graph is concave up. At a horizontal tangent, that means it's a minimum, right? On the other hand, if we get a negative answer, that means the graph looks like this, frowning, at a horizontal tangent. That would mean maximum, see? So I think we can classify right now by just simply taking the derivative again. So I'll write my work in red. Can you see if I write over the top of this? F double prime of x is just going to be 1/12 minus, and you're going to have 1 over 60 x squared, blah, blah, blah. But what's going to happen if you take the second derivative at 0? Moment of truth. What do you get? You get 1/12. Interesting. So notice that the second derivative at 0 is positive. The first derivative at 0 is 0. The second derivative is positive. That's a minimum. We have a happy graph at a horizontal tangent. Okay, so I'm going to go ahead and write my conclusion here, even though I have to erase some of my work. Basically, I'm writing f has a minimum at x equals 0 because f prime of 0 equals 0 and f double prime of 0 equals 1/12, which is positive. 1/12, which is positive. So you've been studying this too. You know that when the second derivative is positive, that means graph is concave up. Well, at a critical point, that's a big clue that it's a minimum, isn't it? Okay, the next, so how would you give a reason? Something like what I just wrote. Okay, write the fifth degree Taylor polynomial for g about x equals 0. The fifth degree Taylor polynomial for g at x equals 0. Okay, so we're supposed to find the fifth degree Taylor for g, right? And this is at 0. So what's the formula? Question?
Does degree mean that it's going to be x to the fifth,
Mhm.
or that there's going to be 5 terms?
Means it's going to have an x to the fifth. That's exactly what it means. So that may happen on the fifth derivative, or it might happen sooner. Or it could actually happen later in some cases. But let's take a look. So g of x can be approximated using g of 0 plus g prime of 0 times x minus 0 plus g double prime at 0 over 2 factorial x minus 0 squared plus g triple prime at 0 over 3 factorial times x minus 0 cubed, blah, blah, blah. This is how we do Taylor series. It's a g instead of an f. Okay, so we need to find g of 0. That means 1 plus the integral from 0 to 0 f of t dt. Okay, so what's g of 0? Look at the top of the board. What's g of 0? What is g of 0? Isn't it 1? The area between 0 and 0 is, of course, not to be ignored, right? So basically, this g of 0 is 1. That's our first term. You can feel good about getting the first term if you're Taylor. So this is a 1. Yay. We're going to go all the way up to fifth order. We might be able to stop sooner than fifth order, but it's at least fifth order, or at most fifth order. Next is g prime of 0. So let's write our work at the top. G prime of 0 would mean d dx of 1 plus integral 0 to x f of t dt evaluated at x equals 0. Right? You're supposed to take the derivative of this g thing. So when you take the derivative of 1, obviously what happens? You get 0. What do you get when you take the derivative of the integral of f of t dt? You get f of x. Right? So you feel like you're just substituting this x in for your t. So you just get f of x at 0. So you get f of x at 0. In other words, you get f of 0. Okay. Well, f of 0 was actually given in the piecewise function. Look, it's right here. It's negative 1/2. See? So that would be your next coefficient. I'll highlight what I just found. It was buried in the stem. You have to kind of search for it. It's right here. Here's f of 0, see? Negative 1/2. So this is negative 1/2. And then there's an x minus 0. I'll just write that as x if you don't mind. Plus g double prime of 0. Oh, really? Well, that's just f prime 0. Didn't you write down f prime on the previous problem? Look back at part B. Didn't you already write down f prime? See, g double prime of 0 is going to be f prime of 0. It's going to be easy from here on out, you see. Wasn't f prime of 0, 0? Back in part B? That's good news. Wonderful. So this isn't as bad as you'd think. G triple prime of 0, well, that's just the 1/12 that we found. Remember, that's f double prime of 0, same thing. So G triple prime of 0 is just that 1/12 that we had a few minutes ago. Recall, this was f double prime of 0. Same thing as G triple prime of 0. How'd we do? Oh, 2 more degrees.
3 factorial under that as well.
Huh?
Do we need a 3 factorial under that as well?
Was there a 3 factorial under it?
For G.
Yes, we are on the 3rd term of the Taylor, so we need to start putting in our factorials. You don't really need the factorials until you reach this 3rd term. So there's a 2 factorial, a 3 factorial. All right, I'm going to pause it so you can go ahead and find the 4th and 5th terms, and that will complete part C. Did anyone get the next term?
For the x to the 4th? Or like x to the 5th?
Well, we're on the x to the 4th, I meant. Yeah, what'd you guys find for? I meant to say G, 4th derivative of G, in other words, 3rd derivative of f. What'd you end up getting? 0. So there might be an x to the 4th there, it doesn't really matter. How about the next one? Negative 1/30th, right. Okay, and that ends the problem C. So it was a little tricky because what they had us do for f prime earlier was only write out the first 3 terms, but you actually needed more than that because you had to take the derivative a few times. So turns out if you do, you'll end up getting, unfortunately, the 5th term on the 5th derivative. So it's actually the 4th derivative of f. Question?
Are they likely to give us one that's this time consuming?
This is from 2010.
So would they like,
Yeah, I mean, I don't know if they would rethink it, you know, like, if I look at the scale for 2010, I guess I could see whether they threw this out or not. But this is all over 4 factorial. The other thing about this problem is it kind of feels like you need a calculator, you know. I mean, it feels weird to write, you know, 30 times 4 factorial, you know, without actually knowing the value. But you can leave factorials in your answer. They don't care about that kind of stuff at all. But yeah, this was a real test question. Will they still do it? Maybe. The first 3 were more or less given to you. You know, like you already could tell by looking at the problem that g of 0 is 1. The negative 1/2 was given on a silver platter. The 0 was a consequence of the fact that f prime was 0 and at 0. The 1/12 you had already found back in the so you actually got the first 4 of these 6 for free almost. And then they probably should have only asked for 1 more, but they did ask for 2 more. So that was the unfortunate thing, is they had to put 1 more step, you know. Did anyone get that 1/30th? Besides, I got it on my paper here, and then
It's over 5 factorial.
that's over 5 factorial. I forgot to put the 4 factorial in. Did anyone else get the 1/30th? Lauren got it. I'm just curious. Okay, it just kind of depends on how carefully you wrote it out. So, okay, and then is there a part D? Let's go see. The Taylor series for G about x equals 0 evaluated at x equals 1 is an alternating series. It has individual terms that decrease in absolute value to 0. Use the 3rd degree Taylor polynomial for G about x equals 0 to estimate the value of G of 1. Okay, so we basically know that G of x is equal to, and we just wrote it on the other page, okay? So it's 1 minus half x plus 1/12 x cubed. So 1 minus half x plus 1/12 x cubed minus 1/30 x to the 5th, right? We're going to try and find, you know, G of 1. G of 1. I think this is a calculator problem now that I'm looking at it. It's BC number 6. So G of 1 is 1 minus a half plus 1/12 minus 1/30. And I forgot to write the factorials again. This was over, this was 1 factorial? This one was the 2 factorial.
That was 3.
Wait, this was the 3. The 4 was invisible. This was the 5. Is that right?
Yeah.
Thank you. So basically, this is actually a 72. And this is 120 times 30. 120 times 30, 3,600. Okay, so for that you need a calculator.
You only need the first 3 then.
Oh, only first 3. Good riddance. I'm just really hoping not to have to work with that other one. Yeah, so basically 72 minus 36, 36. I think it's 37 over 72. Can someone verify that? 72 minus 1. No, 72 minus 36, add 1. I think that's right. Okay, now what is the error? Well, the error would be the next term, right? The first neglected term in this series was that x to the 5th term, right? So that first neglected term was the minus 1/30th x to the 5th. So that, since this is an alternating series, that would be your error. So you can just write max error is, and then write the next term. 1/30th, 1 to the 5th, all over 5 factorial. I forgot to write it again. So you can see my downfall is going to be forgetting to copy stuff over. So this basically gives you, we already wrote it down, 1 over 3,600. And they're trying to get us to believe it's less than 1 over 6 factorial, which is only 720. I think it's definitely less than 1 over 720. 30 times 5 factorial is 3,600. So this error is definitely less than 1 over 720. So D wasn't that hard, really, if you remember copying factorials over. Okay, any questions on that? And I think with that one, you could have used a calculator. I am so sorry. But we did it with that one. All right. Form B that year had this problem instead. Hey, no fair, only 2 questions on here? So if you take the Form B, you get an easier test? Not usually. And that doesn't mean, just because it's 2 parts doesn't mean it's easier. Find the interval of convergence. I'm wondering if there was like a part C and D and I cut it off, maybe? Well, anyway, you can look online at 2010 BC Form 6, Form B, I mean. But let's take a look at interval of convergence. Let's remind ourselves how to do that. So for that, you just usually set up a ratio test. And you know you really don't need the -1 to the whatever. So I just basically put in the n plus first term, and this is all over the nth term. Or some of you have been clever, you've been just writing n plus first term times reciprocal of nth term. That's a little bit easier to look at. And we're going to force convergence by making this less than 1. And you can kind of see what pulls out. You get a 2x that just sort of pops out here. Don't forget that absolute value. As for other survivors, you can cancel these out because of the absolute value. You basically have an n minus 1 over n right here. N minus 1 over n. Okay, bye, Lauren. So, you're welcome. So your limit right here in green is 1. That's 1. Okay, so how do we interpret 2x is less than 1? Why don't we divide by 2 on both sides? We just get x is less than, absolute value of x is less than half. So let's see if we can read it the way we read earlier. Where's the center of convergence? It should be right next to your x. Nothing there, right? So center is 0. What's the radius of convergence? Half. basically be from negative half to positive half. And so the ratio test is not just a test for convergence, but it also can help us find an interval of convergence. Another reason why people like the ratio test. What about endpoints? I think we should definitely include endpoints if they qualify. I don't think when they asked for the interval of convergence they meant don't even bother with the endpoints. You should look at the endpoints. If there's a less than on one of these, or both of them, if there's equals, I mean, you're going to want to get them on there or you're going to lose a point. Okay? So let's go ahead now that we know the radius, let's test both endpoints real quick. It's not hard to do. This happened on the math board exam too. Okay? So imagine plugging in negative 1/2. This would be negative 1 to the n, 2 times negative half, all to the n, all over n minus 1. You want to play around with this until you're really comfortable answering the question. Okay, so it's negative 1 to the n times negative 1 to the n over n minus 1. Is that an alternating series? It is not. Let me show you why. If you combine the top two negative 1 to the n's, it's negative 1 to the 2n. In other words, negative 1 squared to the n. Negative 1 squared, and then to the n. That's not alternating. This is the series 1 over n minus 1 that diverges by the LCT, actually, or the DCT with the harmonics. So this guy is a harmonic, you know, he looks like the harmonic guy. That is divergent. So diverges at x equals negative half. Let's take a look at x equals positive half. I'll bet you it converges. You know these test writers, they're very clever. Negative 1 to the n, 2 times a half to the n over n minus 1. This time when you simplify, it's a little bit easier. You don't have that extra negative floating around up top. That thing looks harmonic also, but it's alternating. So this one converges at x equals half, you see. So it's one of these like half convergent, half divergent endpoint problems. So I'm going to go ahead and go up here and make my less than 1/2 into a less than or equal to 1/2. Right there in green, I just fixed it. Do not circle your answer until you have tested both endpoints. I'm warning you. Same thing happened on the math board exam last night. Yes?
What would you use to show that it converges?
That would be the AST. The AST. Because ignoring the alternator, 1 over n, or 1 over minus 1, for all n's greater than 2, like it says in the problem, diminishes. It goes 1/2, 1/3, 1/4, and so on. Or sorry, 1 over 1, 1 over 2. So it gets smaller and closer to 0. So smaller doesn't always mean closer to 0. Smaller, each term is smaller than the previous, and that's consistent pattern, and it goes to 0 specifically if you take the limit. So AST, I can write that on here. And let's look at part B and then let's go home. Okay? You can play around with the rest of this stuff later. It's all FRQ stuff from the real exam. Most of the rest of that's FRQ, right? That whole packet? Is there anything else in there? Okay, so my answer was negative half is less than x is less than or equal to half for part A. Justify, that would just be all the work you showed. So make sure you keep it tidy. I erased mine, but show that y equals f of x is a solution to the differential equation. Interesting. Series and diff EQs right there in one problem. xy prime minus y equals 4x squared over 1 plus 2x. How in the world are we going to solve that thing? Well, they actually gave us f. Y is f of x. So this would be x times f prime. minus f equals. So I'm going to goof around with the left side until it looks like the right side. This is like, trig identity. You play around with the left side for half hour and then suddenly you realize, hey, that's the same thing as the right side. Okay, so let's see what happens. What is the derivative of this thing? Don't stress out about it because you can just take the derivative right as it is. Leave the negative 1 in there, leave the n minus 1 right there, just bring down the power and take away the power. So it's just going to be an n and then 2x to the n minus 1. Don't forget the chain rule. Times what? 2 to the n. Be careful here. What you're looking at, this f is a little bit deceptive. Maybe we can write it one time first. It's negative 1 to the n times 2 to the n times x to the n over n minus 1. In other words, negative 2 to the n times x to the n over n minus 1. They did this so that you would watch out for the chain rule. I guarantee you that's their motive. That's why they did this. They want you to notice that there's a 2 to the n here. You got to watch out real close. So I just rewrote my f. This will make it easier for us to take the derivative. We're going to bring down the n, take away power. That's it. No chain rule necessary now. Okay, so this guy is its own sigma. Here's the derivative. It has a negative 2 to the n. It has an n minus 1. But this is n times x to the n minus 1 minus, and then here's the original f in all of its glory. And before you freak out on this problem, you have two fractions with the same denominator. It doesn't get any better than that. Let's just put them together. See this lonely x out front? Hello, Mr. X. Does anyone see another place where I can put him? Can I just bring him inside his sigma? Can I just bring him inside? Yes, I can. Remember, x times sigma means x times a large sum. There's nothing wrong with distributing across parentheses, and this is just the same idea. So you're going to distribute this in, x will become x to the n. So now we're getting like terms. Very cool. Black arrow for the continuation of the work. Before I put it together, I'm going to write it one more time. This is negative 2 to the n times n times x to the n, n minus 1, minus, same sigma, same coefficients almost, x to the n. And now I can put, because these are the same sigma, right? You can make one sigma from the two. It's kind of like integrals. If you have integral from, that should be an infinity at the top. If you have, two integrals, they're the same exact limits, you can just put them together in one integral. The sigma is just a finite version of integral. So put it together into 1, n equals 2 to infinity, and we have negative 2 to the n x to the n times n minus 1 over n minus 1. I factored it. I pulled out the negative 2 to the n and the x to the n. And the n minus 1 cancels. Ah, this doesn't look like the same thing as the right side. Really? Look at the left side. How in the world is that 4x squared over 1 plus 2x? Ah, man. Did we fail? No, it's a G-series. Do you see it? See the negative 2 to the n and the x to the n? That can be put into 1. We'll just call it negative 2x to the n. I'm going to erase because I'm running out of space, but this is negative 2x to the n. This is a G-series. it goes negative 2x squared plus negative 2x cubed plus negative 2x to the fourth. This is a G-series. The first term is negative, it's actually positive 4x squared. The R ratio is negative 2x, and A1 over 1 minus R matches perfectly. What does this mean? It means what they said it would mean, that this F they gave us at the beginning is the solution to this differential equation. So no wonder it was only 2 parts long. It was a long second part with a twist ending there. It's a G-series in disguise. First term 4x squared, common ratio negative 2x. Pretty cool problem. Okay, so I have to head out, but you guys have some more practice problems down there. And I'm glad I picked these two because you see a large variety of ways they can ask things, but there's more. So just keep studying every day, and come see me if you have any questions on anything. Even if I've already given you solutions to a problem, who cares? Just ask anyway, okay? We'll see you in the morning.